Hello and welcome to IGCSE Physics. We're going to look at forces in balance. You have now watched the video on Newton's laws where we give a brief explanation of what Newton's laws are. And now we're going to go to our textbook, page 36, and look at unit 2.06. So we're going to look at forces in balance, guys. Firstly, a force is a push or a pull exerted by one object or another, and also has a direction, so therefore force is a vector. The second thing that we'll look at is we measure force in newtons, named after Sir Isaac Newton, who discovered gravity and the laws of motion, which we discussed previously, and we name the unit of a force after him. Okay, so firstly, there's a few typical forces in Newton. The force used to switch on a bathroom light is about 10 Newton. To pull or open a can of cool drink, 20 Newton. To lift a suitcase, 200 Newton. Okay, and the force of a large jet engine, 250,000 Newton. Okay, first what we need to do is we need to start naming a few forces. So if we look at the boat, we've got up thrust, which is the upwards force of a liquid or a gas that makes something float. We also have the object being pulled down by gravity. We call that weight. All these objects on the pictures have weight, but the boat we can see is illustrating that weight. Okay, so the guy is applying a force through a rope. It's not the physical guy. They're pulling the box. So we call that force tension, because tension is being applied through a rope to an object. So when two objects are connected with a rope, we don't call that force an applied force. We will call it the force of tension. Now the man experiences the same amount of tension as the box pulling backwards, and that tension is in opposite directions. Okay, and then between the box and the surface, because the ground is rough and the box has a rough surface, we'll have friction, and friction is a force that always opposes motion when one material slides past another. If we look at the jet, and it would be similar for a car, we'll have thrust or applied force from the engine, which is the forward force from the aircraft's engine, and we'll have the air resistance, okay, which is a type of friction. Okay, whenever something is moving through air, there's air resistance. We have kind of discussed this before. Remember, if you think of athletes, runners don't shave their legs because air resistance doesn't have such a big effect when you're running and walking. But when you start cycling and going faster than what a bicycle can go, then air resistance becomes significant. Think of opening your hand on a freeway and putting your hand outside the window. When you're driving slow, you'll feel a small amount of wind or air resistance, but the faster you move, the bigger the air resistance would become. Okay, so guys, we can look at motion without force. We have discussed in Newton's second law that if no external forces act on an object, the object will either remain stationary, or if that object is moving already, it will keep on moving at a steady speed. Okay, and we look at deep space exploration and things like that as examples of that. Then, when forces are in balance, this is what we explain now. When there's no external force, it means that the forces are balanced. Okay, so in all these cases, the forces are balanced. And if we look at it, it's not necessarily an object standing still. It can also be, or at rest, it can also move at a steady or a constant velocity. So if we look at the gymnast, she's stationary. The upwards force from the beam, bent beam, is equal to her weight, and therefore the forces is balanced and she is stationary. Okay, if we look at the same ice skater, which has a similar pose or similar position, he is actually moving, but his weight and the force from the squeezed ice is equal. And if he's continuing moving at a steady speed, that means there is no friction between the ice and the skates. Okay, and we know that's not technically completely possible, but in this picture we assume there's no friction, therefore he can move with a steady speed. And then lastly, we have the skydiver. When the air resistance, the air pushing up, is equal to the weight, we reach what we call terminal velocity. And to understand terminal velocity, they explain it here on page 637, but we're quickly going to go to my board. Okay, so guys, there are three stages of terminal velocity. The first stage is when the guy just jumps out of the airplane, he's moving slow, and weight is the only force acting on him. The faster he starts falling, okay, he's accelerating downwards at a constant acceleration. The faster he starts falling, we'll see that the air resistance increases. The weight is still bigger than the air resistance, but the acceleration is decreasing. Okay, and lastly, we get the point where the air resistance is equal to the weight. We call this the state of constant velocity. We also call terminal velocity. Okay, and terminal velocity means that the weight and the air resistance is equal, and there is only now a constant velocity, no acceleration. So if we compare these two motions with the two graphs, a velocity time graph and acceleration time graph, we know that technically if gravity is the only object working, then the acceleration would have been constant, and then we would have something like this. But, okay, we see that this doesn't actually happen. We go from a point where there's acceleration to a point where there is no acceleration, okay, and where basically we have constant velocity. And the point in between that, or the link between that, is the non-constant or decreasing acceleration. If we look at the slope, the gradient decreases until the gradient is 0, and therefore the acceleration decreases. So this would be part 1, constant acceleration, part 2, decreasing acceleration, and part 3, constant velocity when there is 0 acceleration. Okay, I hope you have a good day, and if you've got any further questions, please leave it in the post. Goodbye.